Hello, everyone, and welcome to Analytical Chemistry. I mean PChem. So today we're going to be getting into a short conversation on analytical chemistry topics, specifically activity. So activity is a very important uh, chemical principle that we usually talk about in analytical chemistry. However, today we're going to focus a little bit less on how to use activity and much more upon its origins. So activity is essentially going to be the solution form of fugacity. So we've built up a full set of equations that really helps us describe a solution like we saw last time with colligative properties. But here's the problem. Most of these laws assume that our system is, again, behaving fairly ideally. Either it's behaving as an ideal solvent and follows Raoult's laws, or it behaves as an ideal solute and follows Henry's laws. Well, part of the problem is that most things don't obey one or the other, or even both. So what I need to do is try and find a way to make use of these equations we spent so much time developing for non-ideal solutions. And we're going to pretty much do something very similar to what we did with fugacity, which is kind of come up with a fudge factor. So just like for gases, where we replaced our pressures with fugacity, which is essentially the pressure it acts like, in this case, we're replacing mole fractions with activity. So essentially, the activity is going to represent the mole fraction that the system actually behaves like. So let's go ahead and kind of take a look at this in a little bit more detail. So let's take a look at how we can correct Raoult's law. So under Raoult's law, we make the assumption that I can describe the chemical potential of a system by knowing the chemical potential of the pure state plus essentially RT times the natural log of the mole fraction. So all I'm going to do is I'm going to replace the mole fraction with the activity of the same species. But remember what this equation was actually supposed to represent. This equation was supposed to be represented by the vapor pressure of the system. So specifically, the original equation had RT natural log of the vapor pressure of the real mixture over the vapor pressure of the pure system. And we realize that that actually maps onto the mole fraction fairly well. Well, essentially, we're doing something very similar here, where activity is going to give us the ratio of the pressures that this system actually behaves like. So in this case, if I have an activity of 0.5, well, it means that my system is behaving like it has a ideal mole fraction of 0.5. And again, you can actually get the activity simply through a measurement of the vapor pressure of the system. And again, an important idea here is activity, like fugacity, is really representing what sort of chemical potential the system behaves like, just like it did with fugacity in gases. And similarly, just like we used fugacity coefficients, here we can use the activity coefficient. So our activity coefficient, gamma, is essentially going to be the fudge factor that turns our mole fraction into the activity. So you can also imagine rewriting this as the ratio of the activity to the mole fraction. So essentially, does it act like it's 50% more or 50% less if you were saying looking at a 0.5 or a 1.5? So what we can then do is take this new activity and more or less substitute it in to all of the equations we previously derived. Because remember, the activity also is representing that ratio of partial pressure, the ratio of vapor pressures, which is really what the true thermodynamic equations were all based on. So it turns out that this first expression is by default going to be true. But when I can substitute in this gamma and mole fraction term, I can then make use of natural log laws and essentially treat it as the sum of these two expressions. So what you can imagine is when I'm trying to treat the chemical potential of my substance A, which again is typically going to be a solvent, I can essentially treat it uh, like it obeys uh, Raoult's law, plus this extra little fudge factor that's based on on the activity coefficient. So if you know the activity coefficient, you can essentially come up with a linear correction to what we've already established previously, which is a very useful and simple correction to what's in truth a complex set of equations. And not to mention, one of the important things we should always look for in an equation is that it gets us back to our original equation under limiting circumstances. So in this case, we know that Raoult's tends to hold best when we're dealing with pure solvents. Well, that's a mole fraction of 1. And the closer I approach a mole fraction of 1, the closer my activity coefficient is going to reach 1. Well, when my activity coefficient reaches 1, well, congratulations. What we see is that this term has become a natural log of 1. This whole term drops down to 0. Similarly, we also see this term drop to 0, and our system, again, has the same chemical potential as the pure substance. But again, in practice, the important idea here is that it results in our activity becoming behaving like our mole fraction and giving us back Raoult's. So this is a good way to try and describe solvent systems. But it turns out that solvents aren't all that I care about. I also actually much more often care about solutes. I want to know about the minority component because this is often my active component. So in this case, we typically use Henry's law, which again starts from the same basic principle where our chemical potential is given as the chemical potential of the pure substance plus RT, natural log of the ratio of the real to ideal vapor pressures. Now what we do with, now how we make use of Henry's law is we replace the vapor pressure of the solute with essentially the mole fraction of the solute times the Henry's constant, which is essentially kind of, again, our fudge factor here, which which helps correct our potential. Now, one of the things that we can then do is essentially separate this expression out in terms of the constants, or more appropriately, the values that are described by a given solute to the properties that to our true variable. So what we can do is pull out our Henry's constant and our our vapor pressure for the pure substance. We'll pull that out front, and this leaves a trailing term of RT natural log of the mole fraction of our solute. Now, when we do this, well, all of these numbers are going to be perfectly described by our solute. So we can essentially collapse them into a new constant. So we're going to call this value the chemical potential of the solute. So again, this chemical potential is going to reference what the chemical potential of the solute was if it followed Henry's law all the way to a mole fraction of 1. So again, this is kind of an artificial value. You're never going to reach it because the equation will tend to break down before then, but it's an important kind of reference point. And you'll notice will often be significantly different from the chemical potential of B as it behaves as a solvent. And then again, we go ahead and correct the term with RT times the natural log of the mole fraction of B. And again, our where we are representing the chemical potential of the solute by the chemical potential of the solute as a solvent, plus essentially this correction factor of the difference in between the solute and the solvent energies. And again, it is worth noting that this equation is only going to really hold well as the mole fraction approaches zero. The larger this value gets, the worse that this equation will end up holding. So we want something that will make this equation hold just a little bit longer. So what we do is the same thing we did previously. We replace the mole fraction with the activity. And in this case, our activity still is still the same activity that we had as when we described a solvent system. We're essentially just changing the reference point a little, but it's worth noting that will give you the same answer if you try and stitch these two equations back together. And we can also end up expressing this equation out in the same way that we did previously, where we can replace the activity of the system with the activity coefficient and the mole fraction. And what we're finding here is that what's really going to make the system behave the same as our previous solvent equation is, again, all encapsulated in this activity coefficient, which will help stitch our equations together. And again, it's worth noting that as our mole fraction approaches zero, and more importantly, as our mole fraction approaches zero, our activity coefficient is now going to approach 1, which means that this last term will have a smaller and smaller contribution, which very importantly for us is going to return back our original Henry's expression, which is exactly what we want to see. But it's worth noting when we're describing solutes, we often don't like to use the mole fraction of a solute. Instead, we like to make use of molality, because turns out this side of osmotic pressure, we're really not going to see molarity. So let's go ahead and try and describe the molality of the system in terms of activity. Well, really all we need to do is kind of change our reference point, because the reference point is a little bit artificial. So for example, when I'm looking at this Henry's law coefficient, I'm really referencing the energy at, say, a mole fraction of 1. Well, we can essentially set it to say what's the energy at a 1 molal scenario. And then I'm going to essentially use this RT correction to project that how we differ from that energy as I either go up or down. And so we can essentially substitute the ratio of the molal at our measured for our measured mixture over essentially our new reference condition. So again, our reference condition is typically 1 molal. But we can also end up correcting this in terms of activity the same way we kind of did before. We're going to just add in that same activity coefficient to see how much I deviate from the pre-existing behavior. And this is going to be the same activity that we saw previously. But most importantly, what we've really done is kind of change that reference point, and it still can be very hard to predict what that activity coefficient is going to look like, which again can be kind of problematic. But one of the biggest things I want to make note of as we're switching these reference points is this reference chemical potential is very different from what it was when we're making use of mole fraction. In this case, it's literally the chemical potential at a mole fraction of 1. Whereas here, it's the chemical potential at a molality of 1. So these reference numbers can be very different. So whenever you're making use of these equations or chemical potential species, make sure you are very aware of what they're treating as their reference condition, as this can affect how the equation is used significantly. One of the other things you may have noticed as we've been going through is kind of this mystery of what is our activity coefficient. We've been kind of just treating this as a fudge factor without any information about how to get to it. Well, it turns out that oftentimes we're going to need to determine this through essentially rigorous experiments. But we do have a couple of ways we can get at this activity coefficient for some kind of simplified systems. And when we like to look at simplified non-ideal systems, let's go for a regular solution. So what we can do is use our equation for the Gibbs free energy of mixing for a regular solution, which, as a reminder, is related to a factor based on the uh, entropies of mixing A and B together, plus essentially our enthalpy of excess, which is based on the IMF strength and the frequency of interactions. And again, all of this is modified by nRT. But we also know another way to describe the mole fraction of mixing, which is essentially treating this system as ideal. So I just used the ideal expression, which was entirely entropy driven, and then we substitute out the mole fraction of A and B with the activity of A and B. Now, in case you're asking, why do I use the mole fraction of A and B instead of the activity out front? That's because these expressions are actually based on the sheer number of moles, not on the chemical behavior. These terms are what allows us to pull the N out front. So these guys will stay as the mole fraction, where again, these are modeling the chemical behavior and so are thus expressed as activity. Now, you may notice that both of these give us back the free energy of mixing, which means these two expressions are going to be equal to each other. So I can literally try to figure out a way to relate activity to the strength of the intermolecular forces. However, in order to start, we're going to start by essentially getting rid of the shared terms, most notably the nRT. Otherwise, we can go ahead and set the systems equal to each other with activity on the left and the regular solution expression on the right. Well, we can, when we do this, we can say, well, we can give a little bit more information about the activity. We're going to turn these activity numbers into a combination of the mole fraction plus the activity coefficient, just like we did earlier. And we can do this for both A and B. Now, when we do this, you may notice we have the mole fraction times the natural log of the mole fraction on the left and also on the right. And the same thing with B, which means these terms should drop out of our expression. And that actually doesn't leave us with much left. It leaves us a relationship more or less in between the activity coefficient of A and B and xi are strength of intermolecular forces in between A and B. So we want to go ahead and try and figure out what expression for these activity coefficients will make this true. And it turns out that it's a little bit hard to derive the solution, but we can actually prove a known solution for this set of equations. And these are called the Margellas equations. And really what they say is that the natural log of our mole fraction is going to be equal to the strength of the interaction times essentially the mole fraction of the other species squared. And this will hold for both A and B. All right, this seems a little bit weird, but let's go ahead and prove that this is the case by substitution. So I'm just going to go ahead and substitute in these expressions for gamma and for A and B. And when we do this, well, we get mole fraction of A times mole fraction of B squared times the extent of reaction. That's on our left. Okay, these look a little familiar, but they aren't quite the same. I have two terms here on the left, and I have a couple of squares. So what I can actually do is I can take this expression on the right, and I can multiply it by 1. Most notably, the form of 1 we're going to make use here is the mole fraction of A plus B, which for a two-component system should always yield a value of 1. Now, when I do this, I can multiply out the strength of the interaction times their mole fractions, and we get back our original expression that we had that we had by substituting in the Margellas equations. So it does actually show that that this substitution does end up yielding the value on the right side. So it turns out that these Margellas equations do hold. Now, what's actually uh, and this actually ends up being really cool because it tells us a lot about the activity and, most importantly, the activity coefficients of a species. So let's go ahead and take a look at the activity coefficient of A. So we find out four really cool things. First of all, it turns out that the activity coefficient, so how close to ideality A is, depends on the concentration of B. The more B is present, the less ideal it's going to behave, which again makes sense because the whole premise about ideality was a system is going to tend to behave ideally if all it's surrounded by is itself. And the more other things it's interacting with, the less it's going to behave like itself. But it also depends upon the nature of the IMFs. Again, remember, this xi value is equal to 0 if the intermolecular forces are identical to the to the starting species. So if this is 0, then guess what? It's going to give us a it's going to give us a activity coefficient of 1, which means the system behaves ideally. And the more and more these intermolecular forces differ, the less and less ideally the system's going to behave. Also, this one's a little bit unusual. Both of these behaviors scale exponentially. And this is actually a really kind of important idea because it really helps illustrate how how we can actually behave like a pure solvent for quite a while. We can follow Raoult's law often fairly far into the mole fraction regime, and then suddenly we really don't adhere. And this is all based on that exponential scaling. Finally, and this is actually really cool, we can determine this extent of reaction directly from the enthalpy of excess. And that means that I can determine the activity coefficients from the enthalpy of excess of a regular mixture. So as long as you have a regular mixture that mixes well and evenly, by simply measuring the enthalpy of mixing, you can end up determining the activity coefficients of the system under all mixing conditions, which is huge. We can also make use of the Margellas equations to tell us a lot about, about the behavior of the vapor pressure of, again, these mixed solutions. So we can do this by starting with essentially our Raoult's law variant with activity. So again, this is another way of perfectly describing the activity of the system. The activity, whether it behaves Raoult's or Henry's law, is always going to be related to the ratio of these two, of the true to ideal or pure vapor pressures. So this is always going to be true. We can then essentially substitute in our other definition for activity based on the mole fraction and activity coefficient. We can then make use of the Margellas equation, which says that the activity coefficient is going to be equal to the exponential of our extent of reaction and the concentration of the other species. Now, you may notice that we like to describe our system entirely based on one species identity, in this case A. So we don't really want to have a mole fraction of the other species up top. So the trick we're going to do is, well, say that the mole fraction of B is just going to be 1 minus the mole fraction of A. And so now what we have is an expression for the true vapor pressure of any mixture based on its ideal scenario, how much of it is present, and how much it interacts with the other solvent. So this one we can essentially, the concentration we can essentially just plot for any sort of mixture. However, it's worth noting that no matter what, if I'm looking at very dilute systems, what I'm going to end up finding, as if I have a slow mole fraction, I'm going to approach kind of this ending kind of scenario where the uh, where the exponential term for the mole fraction is now going to be 0. So I get 1 squared, and I just have the strength of the intermolecular forces left behind. Congratulations! You just derived another description of the Henry's constant. Also, and so we're going to end up finding, we're going to have a greater essentially slope for this original behavior for endothermic mixing, which again makes sense because it's not going to want to interact with the other species and it's going to be more volatile. And indeed, we see this as the value approaches closer to like 1, 2, or 3, it gets higher and higher and higher. If you have exothermic mixing and it wants to hang out with the other species, you're going to see this negative deviation because it doesn't want to go. But also, it's worth making note that in all cases, if you have a solvent-based system, what we tend to see is that the mole fraction is going to approach 1. So this whole exponential value goes to 0. So this whole term goes, the whole exponential term goes to 0. So this whole term is either the 0 or 1, and congratulations, we get back Raoult's law, which is the reason why all of these lines always converge to the same point, no matter the strength of intermolecular forces, because there's not enough of the other species to interact with, so it just drops out. So I just gave you a whole bunch of information. So let's try and determine what things look like as I go away from ideality. So one of the big things is that we're going to have several slightly different forms of activity to deal with, and it's all about the reference conditions. So one of the biggest things you can make note of is that one of the equations that's always going to apply is the chemical potential is always going to be equal to the chemical potential of the pure species plus RT ln of A. And this will always be equal to RT ln of the vapor pressure over the ideal vapor pressure. These are our base equations. It's essentially all kind of based around the Raoult's-like expression. What we can then do is essentially change our other conditions to get around the behavior of solute states, whether it's in a mole fraction or a molality ratio. However, and almost always this deviation is going to be primarily driven by that enthalpy of mixing. Most systems behave relatively entropically consistently, but that enthalpic term is going to really drive positive or negative deviations. However, one of the things I want to make note of is that all pure species, whether it's a liquid or a solid, are always going to have an activity of 1 because they always behave like they're pure. Their concentration doesn't change. And fugacity, well, because you're measuring the concentration much more directly through pressure, we get our nice fugacity coefficient, which behaves just like our activity coefficient. So hopefully this kind of makes sense of why we can use all these activity expressions. So next time, we're going to focus in on a specific reason why why we need to make use of activities and a specific non-ideal scenario. We have to deal with ionic solutions. Till then, take care.